editorial team of the journal, and it is a regular held on Fridays. So Harald, you do not to excuse at all. So that is a normal event and is quite often happen in the evening of Friday at 8 o'clock. This is we will invite world famous scholars share the research progress or perspectives. So today we have invited Professor Harald Fuchs from Münster University. This name alone already gave me joy. So Münster in Germany. He has completed his PhD project in material science at the University of Saarbrücken with Professor Gleiter. He's a pioneer in nanoscience. Then Harald spent a postdoc doctoral year in IBM and with in Zurich, and with the group of Binnig, Gerhard Binnig and Roha from 1984 to 1985 for 1 year. You may know these famous names because the Binnig and Roha, they share the Nobel Prize in physics in 1985. So from 1985 to 1993, Harald joined he was the leading person in the water organic films research project at BASF. So we in China, we often say BASF company in Germany. Before he became a chair professor and director in Physical Institute of University Münster in 1993. So he is the founder of the Center of Nanotechnology in Münster, that is Santec, and he is the scientific director since 1993. So the research work of Harald Fuchs focused on the nanoscale science and nanotechnology, ranging from scanning probe microscopy to self-organized nanostructural fabrication and nanobiosystems documented in more than 700 previous peer-reviewed publications and 58 patents. He was the speaker of the first large-scale collaborative research Sino-German basic research project, so namely the SFB TR61, jointly funded by DFG and NSFC. He is also the co-founder of 2 startup companies. He is the elected member of German National Academy of Science, Leo Paulino, the German National Academy of Science and Engineering, and also the member of several other academies. So he received the Chinese Friendship Award of Chinese government in 2019, and the Chinese Government Cooperation Award in 2020. So Harald, so that is now your turn. So welcome to today's talk.
Alifang, thank you very much first for this very kind introduction. And I would like to thank also the organizers, Jessica and Meng Chao, for asking me to come today and give some aspects of our work in Münster and beyond. So I selected this special title, which says molecules at work. It means what can molecules do, from chemical surface reactions, for example, up to something what we could call molecular machines, and maybe expand out of this maybe in upcoming area in different directions. And of course, we usually start with very simple things, and that's why I'm going to talk about a little more in detail today. So let me then first give you the overview of what you see in this picture here. That is the science park, and some of you have been for a shorter or longer time in Münster, but that's how the science park looks like. So we have the Centec, which Lifong mentioned already.
Sorry, Harald. Yeah? I think I cannot see your screen. You.
How about the others?
So I just see you, but
we can see Professor Focus's screen. We can see.
Okay, yeah. Okay. So then this is only my. Okay, that's okay. Now
maybe you start again. Okay. Yeah. So what you see here in the science park is on the left side the Center for Nanotechnology, which we opened in 1993, so 19 years ago now. And then we have different other institutions like the Max Planck Institute for Molecular Biomedicine, the daughter kind of institution, SONS, the Center for Soft Nanoscience, which was opened. I'll show it in a little next slide or so, for soft matter and soft nanotechnologies. And the NanoBio Center, this is more for starting startup companies in the field of nanobio. And the reason why nanobio plays a certain role here is because we have a huge clinical here. This is the clinics of Münster as a university clinics. And also here we have the Max Planck Institute, which is molecular biomedicine, although the term medicine is there. So they are focusing on stem cells and this kind of things. And what you see here, this MIG is standing for multi-scale imaging. That's a new center where this crane is just behind Centec. And this crane is now, of course, disappeared because this picture is now 2 years old. And now there's a big building which is hosting in the end of this year, medical department and people from physics and chemistry dealing with technologies allowing to have new imaging techniques for medicine. So there's quite a few activities together. And so let me then come quickly to what I indicated already, to this new building here, what we have here. And let me see if I can get it here. Yes, this is the SON building, so Center for Soft Nanoscience, just about 50, 60 meters away from Centec. And this was opened, as you see here, in November 2018 as a basic research center. The Centec has also companies, but this one is only for basic research, and with a stronger focus in future also to biology. So the first big event came in 21, where they got a new CRC grant with this number 1429 from DFG, with a starting capital of 10 million euros, starting last year in January. And this money is for the first 4 years. And in principle, as you may know, you have total the possibilities after 4 years to apply again, and then a third time after 8 years, if everything goes successful. So what you see here is a special construction in this building here, where we have a kind of a separate shelter kind of structure, which is partly underground and overgrown by soil and grass. And below that is a special microscopy institution belonging to SON for high resolution transmission electron microscopy and all these systems you need. And we hope that we have here for these special rooms. And this, by the way, is completely mechanically decoupled from the main building. So vibrations from this building cannot couple into this one. So it's very stable. And we hope that by end of this year, we will be able to receive for that labs then the final goal to complete the instrumentation and so on, consisting of a cryo-TEM for doing cryotomography in biological samples, plus another normal bio-related TEM and FIB and the fourth, which will all come here. So that is something that is we are waiting for, but then we can do quite a lot of things in this area in combination with others. So this is a view to Centec again. As I mentioned before, it's a public-private partnership between the city and university. And this wing here is purely reserved for startup companies coming out of nanotechnology or nanobiotechnologies within Zentech. So the regime, the range, what we cover in Zentech, but also partly in Sun, meanwhile, is of course nano-analytical tools. So people like Li Feng and Honying Gao, they were working in this area mainly in terms of the instrumentation, STM, and so forth. Then, of course, the second big area where we all were involved is the molecular self-assembly up to organic devices. I will not talk about this in detail today, but this was some activity together with Deyang Qi, who's also now in Tianjin. Then we have other fields like nanobiotechnology, nanomedicine, working already since many years, but pretty more recent are these two fields here, plasmonics and nanophotonics, and quantum technologies, which are not listed here, and the Münster nanofabrication facility, including high-speed electron beam lithography, kind of high potential transmission electron microscopy in the group of Professor Wilde, clean rooms, and so forth. And now it's going into, in this part here, it goes more into optical computation and quantum technology with a special group, and a new department was just started by the university dealing with quantum technologies. So there will be more aspects coming up in the next years. So if we look at that, I just would like to confine now to what I'm going to tell you a little more in detail today, and there are three topics. So first, I will give you a very short and compact introduction of what we are doing in this area of precision chemistry, on-surface chemistry. And then I will focus on one type of molecule. These are the heterocyclic carbines, which show remarkable properties in terms of their behavior on surfaces, but also in terms of what you can do with molecules. So what I intend to explain with this example is that one thing is the surface reaction, which is included here, that the molecules react with different metal surfaces. But then beyond that, maybe they can do more. And we will see some examples which I find interesting. And then finally, I will give you, because we, as physicists, we always have to do with analytical technologies which we are developing. And I will focus here on, in particular, on low temperature AFM. And on the one hand, working in UHV conditions, ultra vacuum. And on the other hand, an AFM type which you can use in liquids and ambient conditions, but which can be used to write capturing patterns with biomimetic nanostructures to capture rare cells. And what rare cells are, I will tell you later. So this is mainly the focus I have today. And now here comes the first thing, which is just a summary of some highlights in on-surface precision chemistry over the last 10 or 11 years. And I don't want to go into all these details, just mention, you see the titles of the papers, or the papers, the journals at least, where this has been published, and most of these things you can find there directly and read in more detail. I ought to mention that these two things here, these two papers were not done in Münster, but in Nanjing, where we have the Herbert Leider Institute, and we have set up here an STM lab with two people, Hu Hui Kong and Tianxiao Niu, and Hu Hui is doing organic on-surface synthesis, while Tianxiao was, until he left to another place for becoming a professor, he is dealing with 2D materials. So this is a kind of very constructive combination, which we have also with other places. And that's why I show it here. And yes, this I will use as an example later for this AFM things. And this is related to the carbines. I'm talking a little more into in the next part. And yes, and then we have other things which are still in progress, dealing with kind of precursors with Professor Studer from Chemistry Institute in Münster for crafty ion structures, and deeper reactions on surfaces, on metal surfaces, where you can find some very defined patterns. So this is possibly, you have all these parts. The more recent thing is here to try to have a kind of polymerization of silicon double bond systems on a metal surface. And in fact, together with the group of Struder, we could make this by means of a real silanes, which in fact form some double bonds occupied this here on both sides, with the silicon it's located here and here and here. And here we have two phenyl rings on both sides here. And actually they form double bonds, but the funny thing is here, maybe I can show you a picture what the structure, the basic structure is here. So there were different systems, and the best ones were these ones with the hydrogen terminated things, and they can in fact then form silicon-silicon double bonds. And the funny thing here, as the theory showed, that one of the double bonds is kind of mediated by the substrate itself. So it also forms a bond to the substrate while forming the other bond, also double bond, directly from silicon to silicon. And this, of course, could induce another kind of chemistry which might be useful for electronics, because as we know, silicon-silicon is different from carbon-carbon, because silicon as such is a semiconductor. And in carbon-carbon chemistry, like in the carbene or things, kind of things, you cannot make a semiconductor easily because it's a semi-metal. So this is the motivation, if you want, technologically to go into this direction. And this is the theory part of that, which shows the most probable, the most likely pathway in the reaction scheme until we have the final situation as we see here. And what we saw in this little STM picture are these two hydrogens showing upward towards the AFM. And that's what we have seen before. These are these two blobs here. These are the hydrogens showing up in this kind of pictures. So that's quite nice. It also fits to the distances we were expecting. And that's what we published. So from the other papers, and papers I did not show here, you might find in this review article, which is already some years ago, as you see in Nano Today, by Jian Chen and Honying Gao. They summarized all this, what we did, but all the others, and maybe you find more things than I can tell about today. Today, in fact, I would like to focus, as I mentioned before, on one specific molecule only. And this is the N-heterocyclic carbenes, which turned out for us as a very versatile molecular tool. And actually, this is a collaboration with another colleague from organic chemistry, Frank Glorius. He is working in catalysis and other things. And in this context, in the catalytic research, he was investigating these carbenes to combine them with metals. And one day, maybe 4 or 5 years ago, he came to me and said, look, we have understood now in chemistry very well this unit, a metal atom and the carbene, the NHC, the N-heterocyclic carbenes, NHC here. This we understand very well, but we have no idea what would happen if we put this molecule on top of an extended metal surface. There were, in fact, some papers, only a few, in the literature, where people tried under ambient conditions to look at these films. It was known already there's a very strong bond, a single bond from this carbene carbon to the metal atom. And it was known that this bond is very strong, so you can almost not separate this bond easily. It's breaking somewhere. And the question was, what happens if you put this on a metal surface, extended surface, and would it be possible then to image the molecules, because nobody has seen how they really stand or lie on the surface. So it's no problem, we can do this for you. At this part, it was just routine for us to look at a new molecule. This is nothing of physical interest, but it's of course of interest for chemists to see the molecules, how they are oriented. So that's what we did. This was a question, how is it on the surface? And the basic idea was coming from this model here, that these carbines will stand upright on a single bond, yeah, upright, single bond to a metal. So that, well, okay, if they come down from the gas phase, they should land on a single atom, make a bond and fix. And the first molecule we tried is IMES. This has a carbene core, this NHC core. And then it has here a phenyl ring with 3 methyl groups that they call IMES. And the idea is, first you have to protect the carbene before using it by CO2. Then you bring it in vacuum. When you heat it, the CO2 goes off. And then you have a radical system here. And this binds then to the metal. And this works. So he came with that one first because it was available to start with. And in fact, that's what we saw. So the IMS on gold 111 showed this picture, exactly what you expected. If you have a low coverage, then you see all these individual molecules fixed on their position. You see also that they are statistically distributed, and this fits to the simple picture that if you land such a molecule on a metal surface to which it binds very strongly, it gets trapped immediately at the position where it lands. And this is this position where we see them. Yeah? And you also see the molecules look a little elongated. That's because the side groups here are really really big here and large. And this gives them, if they're not rotating, gives them an elongated shape, ellipsoidal shape. That's what we see. It's not a spherical shape. So far, for us, everything was fine, had nothing special, and for us, it was almost done. So they had their picture in chemistry, and they could work on it, and so forth. But then they came up with some new molecules from the same type, but different derivatives. So these two, IPR and IME, look the same. So the core is anyway the same. But here the phenyl ring was modified. Here we have an IPR, an isopropyl group here and here. And the IME is even simpler. It just has a methyl group here and here. Very simple. So we tried without any inspections again. And this was done by Gaochun Wang here. He came from Hanjing's Gauss group as a postdoc to us. And so he came back with another picture, looked like that. This was on gold 111, and the experts dealing with STM realized that here we have the gold reconstruction, the 22 by square root of 3 reconstruction of the gold surface. And on top of that, we see all these molecules. The surprising thing for me was, why are they ordered? This cannot be. Because if you have a strong bond here, why do you see islands like that where all these guys are making a perfect hexagonal order? To get ordered things, you must have mobility. Yeah, we know that these films are very stable, but a stable film would mean you get stuck, but then you have no mobility. Yeah, and for mobility, you would say this may be not a stable film. And this was a good question for the two groups, my own group and Gloria's group. How can we understand it, that we have possibly mobility and stability, which is usually a little contradictory. So to clarify that, we needed some calculations. What you see here in the pictures, even though that you know that STM pictures or the contrast does not automatically tell you this is lower or higher than this was, it looked a little brighter. So these molecules looked a little brighter in the STM picture than this one. This could give, but not necessarily must give, an impression of the height, but you can't be completely wrong. Therefore, you need to do calculations to understand the transition from here to here by changing the molecules all this time. So what they did, this was done by Nikos Stratsinis and Said Ahmedjalaya, two theoreticians. Nikos at the Institute for Solid State Physics in Münster, and Said was a young theoretician who was working in my group. And he's now starting his habilitation to complete it where he is now. And what they found was that obviously some of these molecules, like the IPR and the IME, they can lift out an atom completely out of the surface. And this gives a difference in height as compared to a stuck molecule, like the IMEs. They can lift the atoms only a little, but then they cannot pull it out completely. But if you can pull out an atom completely, then it becomes mobile. And this is demonstrated nicely in a video. I hope you can see it. Let me see if I can start it. First, maybe I have to go. Not so easy. There we go. You see the carbene molecule comes from the gas phase and approaches the surface. One gold atom is now put out of the surface layer. And look at this gray guy. From the second layer, this atom is coming out. And when this atom is removed from the carbene, this second layer atom will close and heal the defect. So the surface is again perfect. And then this is reshuffling in the second layer, but the surface looks perfect. And then this molecule can then attract the atom and makes a bond. Now what we have is we have a situation where we have a strong bond to gold. In principle, the original picture, what Frank was showing me, a single atom, but this atom is now an atom on the surface. It's not free. That means it can move across the surface by diffusion, but it cannot easily leave the surface because we have a pretty high activation barrier to leave for a gold atom to leave the surface. And now this molecule is now using this kind of a ball bearing like structures to move around in the same way as a single atom would move around. And this would explain, if you have many of these things, that in fact these islands of well-ordered structures can form. This is only possible if you have mobility. And nevertheless, the film is stable because it cannot evaporate easily, because you have still this strong metal-metal bond structure here as an atom, which also cannot easily leave the surface, except you heat it up to a higher temperature. So this was a funny thing that looked like this is a funny structure where the reaction led to something that becomes mobile and maybe have some other possibilities. For example, it can get together, can gather together, and then form ordered islands. And then this was then this story where we have seen at the same time around when we had this was a new Star Trek movie where I had this kind of ballbot kind of robots. We have a ball and a head here, and this guy is moving, and then you can bring this cargo everywhere. But it's not only science fiction. In fact, there are research in engineering, for example, at the ETH Zurich, where they actually have they make ballbots, macroscopic ones, not molecular ones. And you see a regular ball. This could be a gymnastic ball. On top of that, they have a gyro-controlled electronics. And you see this guy has a remote control. And this little robot, they call it ballbot, that can bring you maybe a cup of tea or a cup of coffee. Yeah, go between tables very easily and bring you, without falling apart, a cup of whatever you like. But that's why we call this, just for fun, we call this kind of carbene ballbots, which can release a single atom from the surface. So the next step is that, if we go to the other spectrum and say we take not the molecules which can form ballbots, but we take one like the IMEs, for example, which can only lift an atom slightly out of the surface but get stuck, then we would have, in principle, we should see a rotation of this molecule just by thermal excitation. Let's start with the standard symmetry stuff that we had here. So it's looking like the IPR, but this was modified by an hexane coupled via oxygen to the phenyl ring here, and symmetrically on the other side as well. Okay, so then this should see some rotation. And in fact, to see it. Yeah, this is now measured at 5 Kelvin. And you see here, this is what we measure by the STM. And this is the simulation, computer simulation, looks pretty same. And if you heat up a little, you go from 5 Kelvin, from liquid helium to liquid nitrogen, 77 or 78 Kelvin, you see a kind of a typical rotation, which is here not 6-fold, but 12-fold. And this is because you see in simulation, beyond each 60-degree step, you have 2 local subminima where the molecule can jump in with the side arms. So that's why we see here in the STM picture, we see not 6, but we see 12 arms going around. So this potential, when this is calculated, and this was done by Christian Schwermann from theory, you get a completely symmetric potential, but it's known from symmetric potentials. This is a random oscillator. It's not a rotator which can go unidirectional. So it goes during the time some steps forward and backwards. So in average, you see always a kind of rotational structure, but you cannot tell, is it moving in one direction or is it jumping 3 steps forward, 2 steps back, and so forth. Of course, when it comes across the tunneling tip, when you stand here, you see this increase of tunneling current and decrease and so forth. So we have a symmetric potential, and then we get a trivial system which is doing random direction of rotation. That's not what we really want. We want to do more. And then we had to gather together and to what can we do? Well, to solve the problem, you just, for those who are not being so much involved in this field, the problem is the following: why it does make some random walk. If you have a symmetric potential, as the one I showed you, on this real surface, that's a real potential for that system. Then you, for example, you can simplify this potential by a triangular potential, and you put your molecules, let's say here, or your system here. And then you heat it up, you increase temperature, and everything is lifted above the barriers of this potential. It's going up, and then but then it distributes, it can diffuse over the, in this case, it can rotate. That's what it means here. And then you decrease the temperature, and the system falls back energetically, it falls back to its ground state. And then you see in the symmetric case, it's equally likely that you go from this former central point where it started from, either going back or to one of the neighboring potential minima. So you have an equal distribution after some time if you wait long enough. And this means what it shows here as a random walk. Instead, if you change this potential to a ratchet-like potential, which is asymmetric like the sawtooth potential, you do the same thing. You put your system here, you heat it up, everybody goes above the thermal barrier, and then you cool down, and then they fall back. But you see here on the steeper slope, you do not catch as many on the more inclined area, which is weaker in the slope. Yeah. And then you catch more here on these long areas, which has a smaller angle to the normal. And at the end, you end up that you go more and more into a certain direction, in this case, from right to left. So this is a condition to have kind of a unidirectional motion. You need to change the potential. The question is, how can we do that? We cannot change the metal surface because this is hexagonally ordered in our case, and it's difficult maybe to construct something else. But what we can do, we can change the molecule. And this was another piece of work. So we started with that molecule, which is symmetric, this IOMS, yeah, the O stands for this oxygen here. Otherwise, it's more or less and then this hexane groups here. It's the same like the IMES at the very beginning. And then you see the symmetric potential, nothing exciting. So, and Christian Schwermann here, and he went back to his office. He's belonging to Dolcini's group as a student, and he came back after several months and said, well, he tried to simulate a molecule, not knowing, because he's a physicist, if it can be made But he found after several hundred tests of different types of molecules, changing one part here to make it asymmetric. So maybe you can keep that one as shown here, but maybe on the right side, you can put another group. Instead of this group here, you put a naphthalene group, more or less, yeah, and an oxygen in between. And for that, he found this potential becomes asymmetric. You see here a shallow, a very shallow minimum and a deep minimum. This would be appropriate for that as compared to the symmetric molecule. So the question was only, can it be done? And the group of Professor Chloe said, yes, we can do that. And it took them another couple of weeks. They came up with a molecule. And then we put it in, and this measurement was then done by Qindong Ren. He's also back in China now in the National Nano Center. And then we saw that we can see, number one, you can calculate a trace for this molecule. This was also done by Christian. You see it's a random walk around zero. You can have angles of 360 degrees, but in both directions for the individual steps. But if you take this molecule, he predicted that he should get an increase in accumulated rotation angle over time. Of course, sometimes the system makes all the step back, but on average, it makes many more steps forward than backward. Okay, so that was the final test, of course, to see if that is really true. And you see here measurements at 5 Kelvin. And to rotate it, I'll show you it in a second. You have to put some electrons in, some energy in, and then it jumps by 60 degrees to come into the next minimum on the gold surface. And the funny thing is here is the different structures all of a sudden, and you see here the 6-fold symmetry as it should be in this case here. But we also see these elongated structures here, and here's something undefined maybe. But what he did was then to shift part of this combination of two structures apart with the STM tip. And you see what happens is these were two wheels, in fact. Look, these guys are still the reference here and here. And also here, and these two are the reference for that picture here. And if you remove this upper part, you end up with two wheels, which were so strongly entangled before that they could not rotate anymore. But when he moves apart, then they start rotating. And then you see again a wheel, yeah, at liquid nitrogen temperatures here. But here we cannot still see if it is really uniaxially rotating, or is it going in one direction only, or random reaction. And what we then have tried to find out how much energy do we need to deposit to make it rotate. Can we see a real unidirectional rotation? And the answer is yes. And it turns out that we have to inject the energy of the electrons from an STM tip close to this oxygen, this bridging oxygen between the phenyl ring and this hexane aliphatic part. If you put it here, nothing happens. And if you go into the carbene part, also not. And you see, we have many of them. And we will see in a second what happens if we do so. And you see here a little star blinking here in this extended part, which is the aliphatic part. And whenever we put this star, it means electrons were injected by a pulse from the STM tip. And you see nicely it rotates anti-clockwise here. And another molecule, same thing, same type here, is not moving because we are not feeding it with inelastic tunneling electrons. And therefore, the energy is not enough at 5 Kelvin to let it rotate. So actually, the analysis showed that, of course, it's clear that it's inelastic tunneling, otherwise you cannot deposit energy here. But the interesting thing was from the analysis that we need 2 electrons per single hop. Yeah? So 2 electrons charge are needed to be injected to get this. So you can imagine that if you look at the other things, maybe 60% in this case were rotating in the same direction, anti-clockwise. And this is depending on how these naphthalene groups are oriented, because they can rotate along this axis here. And by landing, this phenyl group, this naphthalene group can flip around and get stuck there and fixed by the surface, so to say, in its orientation, or it stays like shown here. And it turned out statistically that 60-something% of these molecules are landing like shown here, and the other 35% have the naphthalene group and the other way around, and they go clockwise. So that is the situation. And if you can separate this, then you can make things which really go in the same direction. The only thing, you have to flood the whole system with electrons such at the right position, and then they can even make a synchronous work, which is not done yet, but I think should be possible. Okay, so this was, and then third question was, what happens if we go away from a flat surface? We take a kind of a working horse for surface scientists. These are the missing row structures. This is very well known. Everybody can use it or use it. And this is number one, the missing row structure, the 2x1 reconstruction, where every second row of the surface is missing. So you have kind of a trench. If it's a top view, if you look from the side, so this row, which should be at the same height, like the yellow top row atoms, is not there. Therefore, it's called missing row. This was, by the way, one of the first structures Binnig and Rohrer were first studying when they started to use STM to find this kind of structures. And here you see an STM picture here, a clean STM picture, 2x1. And there's another one, another reconstruction is called 3x1. Then 2 atomic rows are missing. And then, of course, the width of this structure is wider a little, and we have a small facet here, 1-1-1 facet. And but the width is then 3 atomic units of gold width here, which you have here, have 2 atomic rows distance. Okay, so what happens now if we put these carbines, which are mobile? This was the first idea by side. And what would you, and Anne Backer, what would happen if we put here the mobile types, so this IME and IPR, which can form ball bots? Would they behave in the same way like on a flat metal surface or not? Well, so Anne Backer tried and came up with such pictures. So we saw the 2x1 reconstruction, and it seems that some of the carbines are sitting right on top of such a top row in the reconstruction, but others seem to be somewhere in between or a little to one side. Also here, you see the center is not exactly between 2 rows, but maybe a little shifted also here. So we have these types only. Nothing is seen directly in the trench. And this was then the onset. What is going on here? Why is it certainly going into a 3x1? This should not occur in this way automatically. And then Said came and made a long calculation to simulate this system. And by DFT calculations and molecular dynamics simulations. And after some time, he came back with this picture. So we have seen two types of ball-bot carbines. So the one are sitting on top row. The top row is here marked by this brown colored atoms. Then they have this red colored, which are at the facet, so to say, a layer lower. And then at the bottom of the trench, we have the yellow atoms. So what then happens is that, let me see, that we see that we have these 2 positions. So the green circled ones are belonging to the ones, just to repeat this, to the position where this carbine is landing directly on the top row. And you see here quite a few of them in the real measurement. And the other 3 are colored in blue with a blue ring, and they are sitting somehow in between. It turns out by the calculation, this should be the facet side, here the lower side in the second row, not the trench, because these atoms are kind of buried, so the carbine cannot pull it out. Okay, this was number 1. Number 2 is what happens really. And this was a funny story. So what happens is, if a carbene comes, for example, to one of these red atoms and it binds to this red atom, at this position, when it just bound here, then we put it in blue color, so to distinguish from the other red ones which are not affected by this carbene atom. And if this is a ball-bound structure, it will pull out this atom, right? And that's what it does. You see, it pulls it out, and then we form it. Once it's pulled out, we form it, we color it green, in green. Again, this pull out and moves down a little, and then we color it green. And what also happens, the former atom here on the intact, so this is an intact row, originally all in red. Now we color this single one, which is attached to the carbene, in blue. And here we have the intact top row all in brown. And you will see this atom will follow this defect which occurs here and closes it, leaves behind a defect again. You see it? Now we have this former brown atom is now here becoming red in the layer below. Here we have a defect, and here we have a ball bond, which can now move up and down. Okay, and this defect, as compared to in contrast to the situation in the flat surface, is not closed by lower atoms. And then this dynamics, if you look, what can it do? Well, it can move up and down. It can move here, or it can also move in the trench position, then moving on two rails, so to say. Yeah, this can also happen. And this means these carbenes can remove atoms completely out of that trench and move to microns away and carry this atom away for the moment, leaving behind this defect. Okay. Question is that the only possibility to move, or is there another one? And this you could not deduce from the experiment. You see also the energy here. Yeah? To pull out an atom is 150 or 160 millielectron volts. And to move along the side part here, the facet is 114 roughly. And to move in the trench is a little more higher energetic. It takes 400 millielectron volts by the prediction. So, but could they also move in another direction? And the answer is why not? We can also maybe move normal to the direction of the reconstruction. Should be possible. In this case, this ball bond is not moving up and down, but is kicking out this next atom, like in a billiard game. You kick out the atom, and that is what's happening. You kick it out. You see, go back, and the brown atom, one brown atom, is kicked out, and we color it in violet. Yeah, to see this was formerly a brown atom sitting here. Now the ball bond is sitting here and kicked out this atom. And this guy can repeat this process and kick out more of the brown atoms into the trench. And suppose we have two of these kind of things, two ball bonds sitting in these top rows already, and they do the same thing. So they go to the next one, maybe the one up and the other down for simplification. They both kick out an atom. Then we have two atomic defects, and we have a new dimer of atoms in between. And again, they can move in the trench and kick out again. So what it shows is that these two ball bonds are able to construct kind of monoatomic wires. And if you look at it for the experts, they see easily this forms a new 3x1 added row structure, because here's an added row in the second layer. In the pure 3x1, it's not there, it's deeper, but this is a 3x1 in this direction added row. And that's what happens, and this is what we're seeing. Number one, the formation of gold rods. And it works, if you like a zipper. It gets two separate things together, forming one new row, just for another imagination. And that's what we see here. Actually, these two 2x1 atomic rows are here combined to form one. And here probably we see the activity, not sharply, but this is probably part of the carbene activity here, getting this together. And of course, you would say, oh, well, then I have 50% of the atoms too much. And then you can say, well, this is no problem because we have so many of these carbines around. Some of them will get away, will get rid of this kind of too many gold atoms by moving them as ball balls out of the trench. From this picture, we cannot clearly see that, but if we wait 30 hours or so, we can see that clearly that actually, if we keep it at room temperature for 35 hours, we see more and more like these 3x1 added row structures and getting very long trenches here. And the funny thing is if we wait even longer, for let's say 115 hours or so, we have a lot of these structures formed. And the density of this ball balls gets lower and lower until everything is gone. We believe that what is happening is here, if we have some additional ball balls, additional carbines, they form a kind of a coordinated gold cluster. where we have two, let's say IME carbines, and in the center we have a gold atom. And it's known that this metal complexes can easier remove from the surface by evaporation. That means once these guys have their work done, they lift off and go away. And you are behind with your perfect product, if you want. And that's an ideal system to work with. So from this picture, what I showed you before, it seems that this guy work kind of coordinated. Yeah, they can really do things kind of in the same direction from opposite sides and then form this kind of things. This, of course, because we have billions of these carbines simultaneously everywhere on the surface where you want. In principle, you can, of course, use an aperture and only evaporate a small piece of your surface. By heating, you can also make this kind of structures, but then it occurs everywhere. But here we can make it locally if we want, yeah, because we can exclude other areas and only evaporate carbines on the small area if we need that. So that's a different thing. And the story behind it is that these molecules can do something for us. Number one, they make a surface reaction. But beyond that, they behave like rotators, which might be coordinated if you bring the electrons at the right position. And another thing, they kind of know what to do to make one reconstruction to another one, namely the 3x1 added row. Thermodynamically, what is behind is a downhill process. The whole process is downhill at the end, and that's why it works without bringing in additional energy to work in this way. So that is this kind of things. And then I would like to quickly switch to the other analytical AFM type. This was the third part of my introduction. And that give you two different words, which for us are quite useful. The one is the development of a new AFM tip by Harald, and consisting of a single tetraederally bound oxygen atom to a copper tip. And this has some advantages towards existing opportunities. And the other one is an ambient AFM, which we can use more in biology, if you want, and making structures for capturing rare cells, which can be of high interest for medicine. So completely different things. One is we look at chemical bonds, and the other ones with the same principle, but different types of machines using the same principle go into medicine. So this is a big jump. So on the right you see Harald, and he has decided to, for over 3 years, to work on this kind of tips here. Finally, he had some success to see this a nice dimer here, and these are individual bonds. But there are many things you can find in the literature what came out. So this is using here a kind of a tuning fork tip. So it's a Q+ oscillator, which can be used simultaneously as an STM and an AFM. It is nice and helpful. And the nice thing here is that this covalently bound tip here, oxygen on the copper tip, is very stable because it cannot dissolve easily. You can use it also, and this is another paper which I don't show today, We can use it even at liquid nitrogen temperature, in principle, also at room temperature, but then the noise level is too high. But what it shows, and this was a more quantitative thing, if you look, for example, on fullerenes, and for example, you see here the classical 6-fold symmetry here, and then you can measure the distances. Yeah, there are two different distances. There's this pentagonal sides, we have 1.45 angstroms, and then the hexagonal, little longer sides, we have shorter sides, 1.39. So it seems with this tip, we come below 10% close to these values here. And this is a limitation for the CO tip, which was developed by Leo Gross, who was, by the way, an undergrad student in Münster when he started. And he developed this famous CO tip at IBM. And you see here, because of this weak kind of physisorption, it becomes wiggling when it comes to a barrier, so a little shaky. And this gives misreadings usually in the range of 40% or so in terms of the measurement of bond lengths in cases. Yeah, so it depends a little on the system. It also is limited in so-called fake bonds. When you have this molecule, which was published with two sulfur atoms which are not connected, because it gets stuck here and jumps and makes a kind of apparently existing bond, which is in fact the fake bond is not there. And if you measure this same thing, the same system, and this is the result, then you see a bond which should not be there. And if you measure it, so highly try the same molecule, that's the same thing here with the two phenyl rings, a little inclined. And here we have the two sulfur bonds, and you see they're clearly separated. There's no bond. So it seems to be safer if you have a molecule which you don't know yet. And you can even not tell, should there be a bond or not? You want to know, you have to measure it. Then these more stable bonds are maybe more promising. And the other thing, just to show you one example, is that if you do chemistry, here is two chemistry students, Henning Larsen and from Amido Strudoscope and La Cheng from our group here, they try to measure this one on the different immediates to make on-surface chemistry of diazoketones. And you see it should end up in this kind of molecule, this polyfuran diol biphenyl. And this, yes, we can see that in the STM. This is low magnification. If you go higher, you see more. And this could be that this part here corresponds to this furan diol group, this pentagonal structure, but you cannot resolve more. But now comes a point, because with this probe, we can measure the STM and the AFM at the same time. Here, by the way, you see the intermediate copper atoms here and so forth. And if you switch to the AFM, you see the details on the same position, measured at the same time. Again, the metal atoms here in a different contrast. But here, you can really see the pentagonal and the hexagonal sides here in this product. And of course, you can confirm the things by XPS, but I don't want to go into detail here. But this is the story about this kind of analytical tools, and now we use it routinely. It gets easier and easier to use it. At the beginning, it took 2 weeks to prepare it, but now it can be done by students. Well, the other thing we have done is this writing biomimetic functional structures, nanostructures, and this we did in an external lab, which I had for a long time at KIT and the Institute for Nanotechnology in Karlsruhe. And we were happy to have Michael Hirz, who was a student of Lifong, in fact, when she was still in Münster. And he has a very strong bio-relation by interest. So I asked him to join us in Karlsruhe and to take over this system by a former student, which has left to Stephen Leonard to Florida. He is an American guy. And so he could continue quasi without any interruption. So the basic idea, just briefly explain, is the kind of, you have an AFM tip, you put molecular ink, and we tried already with Stephen Leonard to put phospholipids. Phospholipids are biocompatible systems, which we have in our in our cells. The cell walls are consisting of a bilayer of this kind of molecules or similar molecules, phospholipids. And then they build up with several types of these things, the cell walls. And then we tried to write it with the AFM, and this works pretty nicely, surprisingly well. And then later, by the technique itself was developed by Chet Merkin's group in Evanston and his people, and we used it to first time use this lipid pen lithography also for use underwater. And by the knowledge at the time, it was very pessimistic that this could work, but it worked. And it works like a quill pen. So you dip it, you have here not only one tip, you can have 25 here in this case. And then you can fill this with an ink reservoir. The ink is diffusing here. You dip it down and then you have 25 of pens, which you can use to write. And then you can use all the different colors if you wish. For example, here, 2 different colors, and you ink your different candelabras here with different colors. And then you can do something that you cannot do with stamping. For example, you can write first the red square and then the green square, or this red polygonal structure and the green one, or vice versa. This you can do just by software. You don't need to make a stamp in advance, but the tips can be controlled in X, Y, and Z, and so you can write all patterns. The funny thing is this was made also with phospholipids, colored, marked by fluorescence dyes. And then what they, at the end, Michael did was to combine, to just use a tip and connect these 2 lines, the green and the red lines. Phospholipids are mobile, and you see the red and the green ended up, finally, after they have mixed, the structure is still there, but the colors have mixed, and from red and green, you get a yellow color, meaning that these phospholipids are really mobile, they are fluidic, and then they form this structure, just a proof of concept. So the real thing what could be done, and this was still in the first thing I would like to show, when Steve Leonard was still there, was to use a multi-tip and to write grading patterns, grading patterns and multi-layers, let's say 8 layers of phospholipids. If you find the right pitch, then you have a grading, an optical grading, and then you can make diffraction, of course. But this is not a regular grading like glass or silicon. Here we have a fluidic grading, so you can easily modify it by intercalating it with analytes and this kind of things. And then you read out everything. If you put all these things on a PMMA substrate, it's also cheap. And then you put a super continuum white light laser, you can read out your spectra. And then you can see any change, optical change, which occurs due to spreading of the structures because it's fluidic, or to intercalation, it becomes bigger, or to de-wetting. And actually, we could also see these effects here in reality, meaning that we have a sensor here available, which can be easily written, quickly written, and then used and then throw it away, or you write a new one. And this was done for biotin here, and you see the limitation is around 0.5 nanomolar, which you still could see with this very simple grading. You don't need to buy it, you can just write it. And it's not limited to this kind of structures on a planar structure. And in cooperation with the Institute of Microsystems Technology, also at KIT, we also tried this kind of goblet structures, which they make, and they use it for whispering gallery structures for sensing gases. And you see it here, that is a real structure. So if you heat these mesa structures, which are first flat, and you heat it, you get these goblets. And they form a rim. And this rim can be colored. And then you can color each ring with another molecule, but then you can capture a certain analyte at each goblet. And you can read out this thing optically. So you can have thousands or 10,000s of sensors on a single small wafer, because each one has only 20 microns diameter. And this is a real picture where it's lasing already, colored with rhodamine, and you see this lasing ring. And if you bring in now some analytes, you would see a shift in the spectra. The lasing threshold is pretty low. You see here it takes only something like 9 or 10 kind of nanojoules in order to lase, and the pumping energy is also in the range of a few 30 nanojoule. And this is the real amazing thing. And so that's an easy way how to produce sensors which are from sensor to sensor sensitive to different things. And then you can also multiply these arrays up to 1 million. It's available, and then write the INT. You go out and you see it's more or less uniform. You can write with this 55,000 tips. You can write about 4 or 5 square centimeter nanostructures within 5 minutes. And this is something that is for practical purposes quite useful. And these details are pretty old. You can find it here in these 2 journals when we started with this work. All this is multiplexing colors and the force. So multiplexing was then moved on for practical purposes. It's better to have a polymer stamp, which is not a stamp with a fixed pattern, but using molecular inks, which can then be transferred from a polymer pattern of pyramids. And for that, you take a silicon master, you take PMDS, and then you just cast it on this precursor structure, and then lift it off, turn it around, and you have a polymer stamp. And this is easier to use, and you can colorize it in certain compartments if you want, in 4 different molecular colors. If you have only one, you can stamp 55,000 colors at one stamping. Or you can come back with a precision of about 10 nanometer, or no, less 1 nanometer, come back to the old position and write with another color, let's say blue or green. You write on top of the red ones or the green ones, some other substructures. You see it here, a little zoomed in here. And depending on the dwell time, how long you stay, you could make it brighter or less bright, depending on what you want to do. So with this stamping, we can really produce a square centimeter of nanostructures. Nanostructures means we have about 40 nanometers wide structures in kind of squares or whatever you write. But this can be done macroscopically, once you have a structure in the machine. And the idea was to use this in combination with a medical department in Hamburg, and with Professor Pantel. He is an oncologist, and he was asking us if we can make something for him for catching structures, to find cancer cells, and these are rare cells, in the bloodstream of patients. So he can use these cancer cells, we cannot use them, but we can make the device. And then one of our students was then traveling to Hamburg and to make the experiments together with them there. So the problem is what we have, why does it come into the blood? So once people have developed a tumor, then there are different ways, without going into detail, either by passive invasion or by active invasion, go through the cell walls, through the epithelial, into the bloodstream, and then you have it. And some stops later, after days or so, they can go out again of the vessel and can be dormant for a while. But if they collect at some point, they can form a new tumor, an active tumor. And that is what we call metastasis, and we don't want that. That means we need to detect potential cancer cells as early as possible to avoid this situation. And that's what the medical people want. And so what we did was to write such a fluidic cell, which came from a company outside. This is a basis here. And you see it's really macroscopic. And this is the real sensitive part where we can write with the deep pin lithography, we can write millions of this kind of catching structures, which should be far away from each other, such that the cells cannot overlap on different systems. Next thing is the blood from patients. So this part had to be done in Hamburg. The red blood cells were removed, and then all the rest of everything in the blood, including possibly cancer cells, were marked. So we can mark the cancer cells by so-called EpCAM and RGR2 kind of proteins, which are going into cancer cells or touching on the surface, and then they are labeled. And then we just put biotin more or less on the substrate on our systems, which we can write. And then we let it flow through. making sure that each cancer cell, which is in the blood in this vessel here, has a chance to meet at least one such a catching structure. So once you have them caught, you can take a pipette, you suck it up, and then the medical guys can test what kind of cancer that is. And that is funny. And in fact, these are the real structures where we have cell arrays. And on this biotin catching structures, and you see each landing position is occupied by only one cell. They do not overlap. And that's very important for practical purposes if you go in. And if these are cancer cells, you can now pick them up and you can check, even if you don't know which cancer cell you are looking for example, prostate cancer, liver cancer, whatever, you just can check later by routine analysis what it could be. And that's quite important for practical applications to have an early recognition system where we have an opportunity to identify this kind of cells. So in Karlsruhe, this went to a big thing because you see, we can go from pure basic research situations for making sensors, but also for capturing the structures for cancer cells. So the problem we have here is that there's only one cancer cell in 1 billion regular cells in the blood. So the ratio is 10 to the 9 of healthy cells, so to say, or regular cells versus cancer. And you have to find, like a needle in the haystack, this one single cell. And this is important to do so. And it turned out that what we hear from them, that is even more reliable than the gold standard, which is available by magnetic systems and the force. And the addition, what you have here is you can just pick up each cell later without getting them agglomerated as a big blob, but you can pick up one by one and go to the microscope and see what you have. So what the people in Karlsruhe did, there were two co-workers. They started a company which they called enableinnovation.com. And actually, they are going to produce this diagnostic chip, including the machine, where it can go into virus research, antibodies and drugs, cells and bacteria, quite a spectrum, which they can cover. Well, also for drug screening and development, it would be possible virology, and of course also for bacterial infections. And for that, they use this kind of technology. I did not go in all details here, but if you wish, you can check this website here and get more information. And this is actually a product now where they started at KIT. They're still hosted in KIT, but I guess they will grow quickly now. And in the next 1 or 2 years, I have to seek some space outside. Actually, we have a prototype of this machine also at Centec. So if some of you wishes to join us for a while to test it, you're welcome. Okay, so that is about what I had to tell today to give you some aspects of our work on a broader scale, starting from very small things on the atomic and molecular scale on the on-surface chemistry, then to make one step further to see if you can use these products to make something functional in terms of rotators or molecular assemblers. And finally, also the other side, to be able to analyze this, we need new analytical tools. And this I again showed in two extreme different examples, namely the low temperature UHV-AFM and also the deep-pan lithography, useful for ambient systems for many, many purposes in chemistry and whatever you wish, analysis and so forth. Yeah, and with that, I have to mention that this is not my own work alone, which I'm going to show you, but it's a long list of people in the group. You see here, I think Honing is also online and others here. And I mentioned Harald Mönig with his students here, Michael Hirz with Silvia Sekula-Neuner and Uwe Burg. They started now the company. And in China, I mentioned a few, Hu Kong at NUST and Jinshan from Nanjing Tech, Wenping Hu now at Tianjin University, and other people from theory at Professor Ji from Renmin University, working together with Harry, and Hongjing Gao, of course, longstanding together with Sishu and Dun from IOP, where we still have running projects. And of course, not to forget Li Feng, who contributed significantly to a part of this work we showed at the very beginning, and my colleagues Helmut Zacharias, and I mentioned Amido Studat, Frank Glorius, Gerhard Erker, and also our theoretician in the Institute of Theory, very helpful again, Nikos Dotsinis. Yeah, with that, I thank you very much for your attention. I'm looking forward to your questions and say, xie. Thank you.
Yeah, Harald, thank you. Thank you very much for this comprehensive and very interesting talk. I see a lot of new results. I'm very happy. So now the lecture is open for questions. Is there any? You can ask directly here, or you can write something in the chat box. So
I see something.
Yeah.
Let me see how many we are. Or maybe first the direct questions.
Hello.
So, yeah. So
I have a question. I was curious about the results, why the transformation of the gold 111 surface the transformation is irreversible. You can change it from 2 + 1 to 3 + 1, but it cannot go back. I was curious why.
I think this is a question of the treatment. Usually, this is a pretty stable structure once it's reconstructed, because reconstruction always occurs if you can reduce the surface energy. That's the reason for reconstruction, also on silicon, whatever you take. But once you have reached this system, this is for the surface at a lower energetic state. And there it stays for a while at least, except you have a lower barrier where it can jump back. Yeah, it's always about minimizing energy, in this case, surface energy.
Okay, I understand even if the molecules have leave the surface, it hasn't transformed back to 2 + 1.
No, not necessarily, because it's like if you can also make these reconstructed surfaces by heating. Yeah.
Okay.
Maybe the 3 × 1 is a little more metastable, but the 2 × 1 is very stable.
Okay.
Yeah.
Okay.
Oh, no, it's not stabilized by the surface. So in this case, for our experiments, we first made the reconstruction by heating. If you heat it up to, I don't know, 600 degrees, it starts from the flat surface to become a reconstructed surface, and then you cool down, and then you freeze in this state. Yeah.
Mm-hmm.
And then the molecules, what they did, they made it at reasonable temperature, let's say room temperature, without additional heat. What you also could do, you could also go to, I don't know, 500 degrees, and so then you form a 3 × 1. But you don't need this. These molecular machines can do it. And what we don't know, of course, if you make it locally, let's say you make it on a square micron or 10 square microns, and the surrounding would still be a 2 × 1 or something, what would happen there? This would be another question. Yeah? Can it then, because of some kind of interfacial kind of energetic situation, happen that it spontaneously goes without any carbines or so back to another order? But this is something what could be done separately. Yeah.
Okay, thank you.
Mm-hmm.
So
But the point is that the carbines can do it at room temperature. You don't need any additional heat here.
So any other? So Harald, maybe I start one. So in the first part of this with cabin, you see a lot of this rotation.
Yeah.
That is on the gold 111 surface, if I understood correctly. The first what Gao Qiang made. Yeah. So that was on the 111 gold 111 surface.
Let me check which picture you mean.
From very beginning. So this you may stay here. So this rotation. So it seems that so you talk about the mobility and stability. So that means the molecule can they pick up a gold atom and then they can rotate. So how about in this case the translation, not the rotation mobility, but also translation mobility. Is there any hints for that?
Yeah, of course, because what happens here, though, at this point, we were not talking about rotation at all. This came in a later step. So when I showed actually this picture, and this get me later to the point that it should be a nice rotator, but not in this situation.
Yeah, okay.
But in the case of the cabins which are getting trapped.
Yeah.
It's not included that this also rotates, but a rotator which is a moving target is difficult to observe. That's why.
So they can move.
They can move
with a low barrier.
Yeah, because
barrier.
It's a barrier of an atom. You see, if you compare this distance here with this layer versus this one, it's exactly the same. So what the molecule does, it actually generates an atom.
Yeah.
But if you have a free atom,
this atom can move somehow freely.
Yeah, like by diffusion at room temperature. It's like almost normal atom. And we know this from silver, from copper, from all metals. They move like crazy at room temperature, right?
Yeah.
Sometimes you even cannot see them in the STM.
Yeah. Is anyone try to calculate the moving barrier for in this situation?
I think
it is just.
No, it's just this was at this point not of so much interest. So it should behave almost like a free particle. Maybe it gets some modification, but it seems that the mobility is quite high, like a normal atom. And that's why we called it a bulb, because this guy is moving something somewhere else. Yeah.
Okay.
At this point, it was not so much the rotation, because the rotation we cannot observe, because we need some energy to pump in, and then it moves out already while we are looking. Yeah. So the mobility of free atoms is too high, and therefore it is more interesting to have a fixed structure where this, like in the second case, where we have a molecule which is getting stuck. Yeah. And what I mean with mobility versus stability is the following. The mobility is now clear. I think the atom can move around and carries this cargo in terms of a molecule. It's a new thing which can do something else. Yeah. Here we don't need any further synthesis. We just bring in the molecule. The molecule knows how to do and what to do. It catches a molecule, an atom. Or it catches an atom and gets stuck.
And then they can move freely.
And they can move freely. Yeah. So this is a mobility term.
Yeah.
And stability, this was a puzzling thing at the beginning, because it was known that the cabins, once they bind, and the people at this
they cannot move. Yeah.
They cannot move.
Yeah.
But they are very stable. But here we have a case where it can move and are still stable, because the absorption energy of an atom is quite high. Usually at room temperature, they cannot desorb. You need several degrees, 600-700 or so to get off. And this means stability. You still have like a rail in your curtains in your office or your home. Yeah, you have a rail, and the curtain can only move very easily along the rails, but you cannot put it down except you put a very high force.
Yeah.
And that's the same thing, but this is two-dimensional motion.
So the second question is might be more general. So what is your opinion? So in which direction we did a lot of this on-surface chemistry. So what is your opinion to which direction will this on-surface chemistry lead us? So we see a lot of chemical reaction, we see the movement, we see the structure. Yeah. So then what could be the next step?
So one thing, this was why I showed it today, is a rotator is of course demonstrated in many other molecules. And most of them are flat-lying molecules or not kind of this kind of fixed in one bond, yeah, which makes it for me also very attractive to look at this point. But I think behind that, I was more surprised of this idea, which we first could see when we had the simulation, was this kind of autonomous behavior after the reaction in the reconstructed surface, that they start to shuffle around the surface and make a new one, which is useful. The question could be, for example, can this mechanism be used in such a small scale restructuring, which you cannot easily do by lithography, would be too expensive, but just by evaporating a molecule, and the molecule locally is reconstructing our surface, which might be, for example, catalytically much more interesting than the original surface. Otherwise, we need to go.
That makes sense.
Yeah, something like that. Yeah.
Okay. Good.
So that's what I think.
So
you can try.
Maybe.
There's a question in the chat. Yeah.
Yeah, I see there's one question. So
one question from Wang Xing and another question from Professor Cui Shuxun.
Yeah, should I read?
Yeah, please. Yeah.
The question. So I think this is from Wang Xing. Thank you, Professor Fuchs, for your wonderful report. It is amazing chemistry on surface. My question is, what can carbene molecule carry gold atoms away from the surface?
Yeah. So
whether a special driving force is required? Okay, so this is the question.
So it seems, and this is another interesting aspect. We saw this after the reconstruction action of the carbenes, and these were ball type carbenes. So what they have is a gold atom and the carbene, right? So this is maybe my mouse here is a gold atom, and we have one carbene on top. So what happens in these cases, and we observed this in other contexts, other papers, that at some points, two carbenes can bind to one gold atom, one here and one here. And once you have this kind of coordination bond system, this has a pretty high vapor pressure. So the barrier for that binary system is much lower than for the single bonded gold carbene system. And if you wait, I said something like more than 100 hours, that means half a week or more, then we observe that even at room temperature, these guys start to go into the vacuum. And this is different from a naked gold atom. This would not do that. It goes to the next step edge and it gets trapped there at room temperature at least. But when you have two carbenes, then the energy, thermal energy seems to be enough to get eventually some of these guys off the surface, and then you pump it off. That's the mechanism how it's cleaning up itself. It could be nice. Yeah, you don't need to clean later. You just wait or heat it slightly, and everything is done.
So I think this is really a quite interesting aspect. So use the molecule itself, then let them do something.
Yeah, this would be nanotechnology as it should be. Yeah. Mostly we need huge machines like e-beam lithography and then etching and then blah blah blah. And here we can ask, at least in this example, I think we can ask the molecule to do one useful thing.
Yeah.
Once you have done the work, they disappear. Perfect.
It's the molecular cleaner.
Yeah, it's it's a tool which kind of knows when the work is done because there's no reconstruction to do anymore. And then it finds, because there are still other molecules there which can make the dimers, yeah, in this coordination bond, and they develop a very high, or let's say a very low desorption energy, yeah, and go.
So, any other questions?
Yes. First, I am very enjoyed in your report, and here is my question. I think it's an interesting thing that I think the cluster will maybe have the similar behavior with a crystal of the gold. Maybe a cluster of the platinum, and we treat it with NHC, and will it be have the same process with gold 111 surface, and I think it will have a smaller barrier between the gold 111.
I think thank you for this question. It's a very interesting suggestion as well. So what we should consider in all this kind of surface reactions. So some reactions work very well on gold or on silver or on copper. Sometimes things work, let's say, on silver and copper, but not on gold and so forth. We did not try platinum so far because for most of the things we wanted and needed to do, these major three metals were more than enough to find some new things or found something what we predicted from theory. Platinum, in practical terms, is a little more difficult to prepare. You need longer times to do it, but there's nothing against trying. Once you know that it works in principle on one surface, you can also try on another surface. Yeah. But it's not clear if it would work in the same way. On the other hand, you can say, well, you can also not exclude that it works in another direction, which is also of high interest. So I think that's something one has to try. So of course, you can also see if you can calculate first what you can expect, and then still see if you can confirm it by the experiment. So nowadays, it's no longer easy to say which one is faster, the experiment or the theory.
Yes,
but in any case, in this field, we need always the combination of both. Sometimes experiment is first, see some new effect, which you cannot directly interpret from what you see in the STM or AFM. And then you need theory, or theoreticians are coming up and bring in a new idea, and you can selectively try to find the specific aspect what they predict. So that is a question of kind of very strong communication between theory and analysis. But coming back to your platinum, if you have an opportunity, you should try. Yeah.
Thank you. And I have another question. And if we have the control of the HC molecular, for example, we have a long alkyne, and we can control it by moving it, and will it like the molecular left, for example, and we can move it by control.
Yeah, this was somewhere written. I did not mention everything what was on the foil somewhere. Maybe I think here Syed mentioned that somewhere on his last foil here. It's exactly what you say, that we outlook, here is an outlook by him. This was Syed Ahmed-Jalaya. Is it outlook as controlling the restructuring by external input? That I think what you mean. So the question is, can we modify the molecule that we, in addition to what we do, usually we just use either electrons by the STM for making the rotational aspect, or the function, or use we could also think about light, depending if you make a cis-trans isomerization, changing the quality of certain carbene in a different way. But this is exactly what he also suggested, that this would be, once you have this assembler, can you give him a kind of another additional side group or whatever, that this kind of very small things can move in another direction, or that you can control it from outside somehow, in addition. Yes.
Yes.
The question is only, what is the best way to go? So you need, maybe these things might not be necessarily confined to the carbenes. It could be that other molecules do similar things. So we have to think about it. And possibly you had these things already in your hands, but you need some connection to what comes out, or to realize a certain effect which you don't understand, and you start digging and digging, and then you find new effects. That's normally happening. And then at some point, of course, you need again theory. Yeah, but I think it would be a good approach. Yeah. Coming back to Le Fong's question, it's of course, I also think that the nanotechnology. So I think there's a lot of things to do in our area, surface chemistry, because there's so many things which cannot be done in a beaker, in a gas phase, and we have seen tons of samples where we could all of a sudden we could do this reaction and stabilize it by the surface. This is one thing. There's certainly technically some things to be improved. But then personally, I think also, and this is kind of a hint for that, the reconstructed surfaces are not really flat. That means they're going a little away from the strict 2D structure. And I think if we want to have more intelligent systems like the simple ones here, maybe we have to find ways how to assemble systems which have 2+ dimensionality or 3-dimensional dimensionality, and even being flexible in their responsiveness. That means if you change the condition, whatever could be light or electrons or pH, then can also change their mind and go somewhere else or do something else. But this is a very general statement, and I think this would be the question is how to make it, and how stable would that be. But this would also mean that we need other tools, because 3D systems, when they are complex like proteins, they are typical examples, or molecular motors in the cell. This is something you cannot easily investigate with STM or AFM. So you need maybe other approaches.
Yeah, sure.
This is just a technical thing, but you can use maybe electron microscopy and study the 3D structure, the functional structure.
Yeah, in fact, for here, this reconstruction story, I think that's quite interesting. If you look carefully, this 1/3, the row is not really free. So you cannot find, I guess, just from seeing here, there are no rows without any molecules in it. So not really free. So, but there are still enough space there, empty space. And this empty space can be used, because we know this 1/3 has a higher reactivity. So there's so maybe because here you have space, and it is stabilized by some molecules in between.
Right.
So this may also go back to the first question what Sifan Yu asked. So why this reconstruction is not reversible, irreversible? because if I see it as correctly, there are almost, if you check every row, so they are not totally empty. There are always something there. So that, but it's still free enough to allow the other molecules get in. So that might be an interesting part.
Yeah, but they can come from all sides, and you also must know that we evaporate from the top. It's like a shower of rain.
Yeah,
so
there's still.
So
I mean, this is a then more reactive space. So that can be used for the other reactive chemistry.
So if you wait longer, or maybe if you would heat slightly, then maybe there form these dimers, and then maybe after some time they're really gone. And then you have to
use other molecules. Yeah.
Or use other molecules, of course. You can then use it and take it as a catalyst somewhere, because the 3-by-1 is slightly more reactive.
Yeah.
The only thing is what I also said during the presentation. Usually, if you take a single crystal and you make a 3-by-1 or 2-by-1, it's everywhere. But here we can take a small kind of aperture, which is maybe a diameter only of 12 or let's say 10 microns, and we evaporate only through this aperture. Still, of course, they can diffuse around, but the majority would stay there.
Yeah.
Then
the measurement was done, I think it's also at low temperature in nitrogen temperature, but they do not go back to the original 1 by 2. Yeah. So that's
this is an added row structure here. Yeah. So, but it's the possibilities are quite nice if we take in consideration that we have here some tools which cannot be much smaller. And the question is only what else is available in similar structures or systems leading to the very cheap reconstruction of a metal surface. Because this could be a mass process. You just need to evaporate something, and then you wait. Maybe this is a limiting factor for industry, but this is something engineers will find a way to clean it up without taking, without touching, maybe with other molecules which bind to them and pull them away like a balloon, and then pump it off. So, but this is just a kind of a story. But the amazing point is, and that's why I showed this example, that the molecule as such, you would not consider as something more interesting like the former thiolates. The binding here of these guys is much stronger than the thiolates. And the thiolates used to bind with, let's say, on a gold 111 to 3 gold atoms. And they made the surface defects, which does not occur here. We have seen this in the simulation. In the not reconstructed surface, they don't make defects. You don't see them effect in the STM, because the second layer, the atomic layer, is pumping repairs. I mean, this exactly does not happen in the reconstruction, and that's why they start to shuffle around and get rid of the too many other atoms, or 50%, by going along the wall. So some of these carbines are just being transporters to get rid of the surplus atom or molecules and atoms with them, and others make this kicking out of the side way. And this is really funny. And if you have only 2 or 3 of these kind of molecules, it would not work. You need just billions. There is statistically is always one guy around the corner and sees some thermodynamically some less energy if he does it than that. And then it works. It's not necessary to a number.
So is there any more questions, comments? So I saw Hong Ying is also here. Any questions?
Yeah, maybe I ask one question about the.
Okay, so I catch you.
Yeah, I noticed, in fact, in the recent years, the heterocyclic carbines is very hot for chemists, and also there are many STM groups. They performed the carbines and silicon surface and also on the copper surface to see the magic number effect for the assembly of the carbines. And I see in your group you have the very nice examples for the physical investigation on the carbines. But other groups, they also interested in the chemistry behaviors of the carbines. Is there some balance to see this physical properties investigation and also parallel developed with the chemistry development for the carbines? I mean, for the future.
Yeah, sure. But so if we, of course, now we are at this stage, we can go to our friends in organic chemistry and ask them to make, for example, for the rotator, this was a clear aspect coming from physics, in particular from theoretical physics, saying if we can make this molecule, if we would have it, we should see a rotator. And they made it.
Yeah.
It was not preformed because Christian was investigating several hundreds of different possibilities of making the molecule asymmetric.
Yes.
It's not meaning to make the molecule asymmetric in structure, but to make it asymmetric with its behavior and the surface potential. Mm-hmm. There we should have, an asymmetric potential. This takes so many different attempts, theoretical, on the computer. And finally, then this candidate, he said, should have a shallow and a deep minimum, and they could make it. So I would say yes. In this aspect, it goes in two directions. So in one direction, they come up and want to see something, if something is polymerizing, blah, 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 or to see if that is possible and how they behave on the surface. Mm-hmm. And on the other side, because of course in physics, we want to see beyond the reaction itself, can it be useful? And what is the energetics or the thermodynamics and kinetics behind it to understand it as a physical tool, as a nano tool? Yeah. Yeah. But you're right. This is certainly, if we look at this, it can be done many. But you also know how much time it needs for one question.
Yes. I mean, maybe in the future we can ask chemists to add some fluorescent group to these carbines to make these carbines not only movable on the surface but also shining light. I mean,
yeah, maybe, yeah, sure, yeah, we can
use the STM-induced luminescence or TERS to determine.
I think this is
this carbine.
Yeah, I think with the concept of computational chemistry, I think. In future, this thing will come more and more, as you say, that if you have an idea that, look, how can I make this guy make a kind of a molecular LED, something like that, with a very high efficiency, or solar cell. And then you could sit down, I think it's already possible, you sit down and say, if I want to have this get the guy stuck, he doesn't need to move because I just want to have a luminescence effect. Mm-hmm. What kind of transitions do I need? I have to go from a ground state to an excited state and come back. Yeah. And then is it realistic? Can I do it in the presence of the metal surface, of course? And I would say possibly yes, because this is not a molecule lying flat on the surface, on a metallic surface.
Yes.
So if you go away, and maybe you can put even a spacer in it, and then you're standing very stably, and still on top you have something that can make some luminescence effect. Why not? Yeah, you're right. But this is, to a large extent, I think it could be done on the computer, because at the end, before you can convince a chemist to sacrifice half a year of synthesis,
yes,
you have to come with very good arguments to get it done. Yeah, this is vice versa. Also for us, if they would only come and say, okay, can you make a picture of our nice molecules? We do that. And also with the carbine, this was the first attempt. Yeah, this cost us only a few days, and then we can. But then it turned out, oops, there are much more that they could not know, we did not know. But at the end, this was a great collaboration. Yeah. But as you say, I think write it up, and then one could think about how can this be realized.
Yeah.
then we need guys like the Nikos, Neugebauer, and but you also have it in China. We have to convince the theoreticians first to simulate it, because out of maybe that is a problem in chemistry. If you make trial and error, then you can make 10,000 tests, but the 10,003rd was the real one.
Because this cabin, you see, when it is rotating, this cabin is standing very strictly under the surface. I think if we adding some fluorescent group on the top, maybe the luminescence could be realized for single carbene molecule luminescence combined with some fluorescent group.
Yeah, absolutely. Yeah. It should be possible maybe in the side arm, but then you have to double check if this double potential or this asymmetric potential is still there. But anyway, I think it's independent of the rotational. Maybe you don't need the rotation, you need the luminescence. If you have thousands of these guys, I don't know. And there are other things which are even more funny. If you look at the fireflies in nature, these little luminescing flies in some areas where they have in the night they are flickering. And the funny thing is, these guys, without knowing each other, can synchronize their activity. All the trees are not flickering; they are flashing at the same time. The whole trees. This is fantastic. And Stefan, you remember this discussions with Rudolf Friedrich about getting gradients, some energetic gradients into the system, and they start to synchronize. And this would be another question: can we use this kind of systems and take some Honying's idea to put some luminescent stuff which is blinking, possibly as a molecular system? And then we manage somehow that these guys, under which condition can they blink together, synchronize it? And what does it do?
That will be fine. You just need a detector. So you switch here and then you suddenly see the area, the whole area becomes, that would be fantastic.
That's what I mean with functional things. And it's really could also be used maybe in other directions as detectors for something, and get a control about the directionality where the exciting effect comes from. I don't know, but I think it's a lot of things is done, but it seems we have to leave a little from the 2D world. And beings are almost 2D.
This carbene may offer some possibility because it is standing, and then it can go to the
not the only ones, but at least
the third direction. No, not exactly this one, but the base is there.
We had this already with the densely packed thiols. When you wait, you have almost standing maybe 35 degrees, but this was already a non-2D structure. But you could not have it in an isolated system, then it falls down.
Exactly.
Breaks down. But here they are really stiff systems which can be used. And in the rotator, I thought if the naphthalene group flips from left to right, you get either clockwise or anti-clockwise. So this could be possibly controlled.
Very interesting. And enough to do. Still.
For the next 50 years, we can try something.
So I do not see any question in the paste. So if it's not any other urgent questions, so I think we can stop here. So there's a quite long time in the Friday afternoon and Friday evening.
At least for you guys.
So thank you, Harald, for your great contribution to this event. So I would ask if the other organizer would they have any So announcement or so Mengjiao. So Shifeng, it's your turn. Yeah.
Yes, Mengjiao.
Thank you. Thank you. We have a wonderful night with lots of nice discussions. And thank you again, Professor Fuchs and Professor Chi. And we have an announcement of the next talk by Frank Caruso, Professor Frank Caruso, and in mid-May. We'll come next time. And thank you all for coming.
Okay, thank you. Harald, so I just take this opportunity. So go to your WeChat to check. I just leave a message for another invitation for the talk. Please check that and then give me an answer.
Oh, okay. Okay. Thank you. Thank you all.
Okay.
It was a wonderful.
See you guys.
Also
See you.
technically
Thank you.
today,
Thank you.
Thank you.
Bye.